Welcome to this explainer. Today, we're taking on something absolutely massive. We are going to look at the colossal, genuinely awe-inspiring engineering of YouTube, which is, without a doubt, one of the most complex computing environments on the planet, and we are going to shrink it down. We're translating that whole hyperscale architecture into a highly actionable 12-week blueprint for a 5-student capstone project. So let's jump right in.
Now, you might be wondering, how on earth do you build a hyperscale-style video platform in just 12 weeks straight out of a dorm room? Well, before we can talk about how your team is physically going to build this thing, we have to study the giant first. We really need to understand how YouTube itself handles the heavy lifting of modern computer science, everything from crunching massive video files to managing a global database.
Here is our game plan for today. We'll start with the giant, then look at the translation for your project, build out the pipeline, assemble your squad, and finally lock down your 12-week roadmap.
Okay, step 1, the giant. Let's take a look inside YouTube's actual architecture.
To really appreciate where we're headed, we have to look at a massive roadblock YouTube hit in its early days: data bottlenecks. Early on, YouTube was basically a monolith running on a single MySQL database. Pretty simple, right? But as millions of users flooded in, standard single-threaded MySQL just could not keep up with the insane amount of writes, uploads, comments, view counts, you name it. The lag was getting severe. So to survive, the engineers turned to horizontal sharding. Basically, they took those massive, overloaded single tables and divided them across multiple databases based on specific keys, like a user's ID, to spread out the operational weight so the whole thing didn't just collapse.
But here's the catch. Voicing developers to embed that complex sharding logic directly into the application code? Yeah, that was an absolute nightmare. It was operationally untenable. So to solve this, YouTube birthed a custom system called Vitess. Vitess is brilliant because it completely abstracts all those complexities away. It lets developers interact with a massive, distributed, sharded database cluster as if they were just talking to one single logical database. I mean, it was a total game changer.
But storing the data was really just half the battle. Think about the video files themselves. When you upload a raw video, it has to be decoded and re-encoded into multiple different resolutions and bit rates. The computational heat generated by modern video codecs was literally so intense that traditional CPUs were just choking under the pressure. Google's solution? They actually went ahead and built custom silicon. No joke, they engineered custom application-specific integrated circuits, ASICs, called Argos VCUs, specifically designed just to handle the intense processing workload of video transcoding.
And finally, to keep you glued to the screen, we have to talk about YouTube's recommendation engine. This is a masterclass in handling millions of pieces of content. They use a 2-stage deep neural network. The first stage is candidate generation. This is basically a coarse-grained funnel that filters the entire massive corpus of videos down into a few hundred personalized choices. Then comes ranking, which meticulously sorts those survivors. And here is the real secret sauce. They don't just optimize for clicks, they optimize for expected watch time. Watch time is just a far better proxy for genuine user engagement.
All right, moving on to step 2, the translation. Let's talk about your academic constraints.
Unless your team has, a spare $1 billion lying around for custom ASICs and global server farms, we have to play a slightly different game. We are going to map YouTube's massive enterprise solutions directly to clever, scrappy local tools that'll help you achieve the exact same structural goals. So where YouTube uses Vitess, you're going to use a containerized local PostgreSQL database. Where they rely on a global CDN, you'll spin up a local MinIO container for S3-compatible storage. And instead of custom silicon VCUs, you're going to deploy a dedicated FFmpeg worker container to handle all your transcoding.
But listen, to ace this capstone, you have to strictly follow the rules of the game. Your entire platform must be fully containerized via Docker, and it has to launch with a single command. That means absolutely zero cheating with managed cloud services, no AWS, no PlanetScale, everything happens locally. You also have to prove you can handle multi-user concurrency without any database conflicts, and your security needs to be locked down, HTTPS for backend connections, and strict use of .env files that are kept totally out of Git for your credentials.
Which brings us to step 3, the pipeline. This is all about event-driven transcoding.
So, picture this. How do you process hefty, gigabyte-sized video uploads on a student laptop without completely freezing up your main backend API for everyone else? You do it with an event-driven chain reaction. First, the client uploads their raw MP4 directly to your MinIO container using a pre-signed URL.
That single action triggers your backend to instantly publish a message to a local broker, something like RabbitMQ. Then, a background worker container silently picks up that message and runs the heavy FFmpeg CLI commands to generate an adaptive bitrate ladder. Once it's done, it saves those HLS chunks, the tiny playlist files and video segments that make streaming possible, right back into Minio. The beautiful part? Your main API never skips a single beat.
Okay, step 4, the squad. Let's break down your roles and modules. You have the architecture figured out, but pulling off a complex microservices application like this requires a perfectly structured squad. Your project README has to explicitly document these mandatory roles. You need one product owner to define the vision, one project manager to track the timeline and clear roadblocks, one technical lead who completely owns the Docker architecture, and 2 developers who are going to focus heavily on the front-end UI, the back-end logic, and writing those tricky FFmpeg scripts.
Now, why structure the team so rigidly? Well, it all comes down to a very specific magic number, 14. To guarantee the absolute highest possible grade on this project, your team's chosen development modules have to add up exactly to 14 points.
So how do you hit 14? You do it by strategically stacking your workload. You'll tackle major 2-point modules, like building out that back-end DevOps microservices architecture or creating a machine learning AI recommendation system. And then you pair those with minor 1-point modules, like building a file upload system or wiring up an ORM, an object relational mapper, to interact smoothly with your database. Stack them up, hit exactly 14, and secure that grade.
Finally, step 5, the roadmap, your 12-week execution plan.
How on earth do you sequence this massive build over 3 months without burning out or worse, completely failing? You stick to a strict 4-phase timeline. Phase 1, the first 3 weeks, is purely foundational, getting Docker up, the ORM configured, and standard user management running. Phase 2 is the heavy lift, building out that core event-driven video pipeline and the microservice worker. Phase 3 brings in the interaction, adding things like chat features and the AI recommendation endpoint. And finally, Phase 4 is all about compliance, testing, and documentation, rigorously testing multi-user concurrency to make absolutely sure you don't have any nasty race conditions.
Now listen, to survive a build this fast-paced, do not try to reinvent the wheel. You've got to rely heavily on targeted learning resources. Dive into Martin Kleppmann's book, Designing Data-Intensive Applications, to get your database schema right. Check out Alex Shu's Byte Go for some incredible visual breakdowns of system design. And of course, you're going to want to keep the official FFmpeg and Docker Compose documentation open in a tab at all times. Seriously, they will be your absolute lifelines when you're trying to network all these containers together. And that brings us to the end of our blueprint. We've taken the incredibly complex hyperscale engineering of YouTube and translated it into a totally accessible, step-by-step execution plan. You've got the architecture, you've got the Docker pipeline, you've got the 12-week roadmap. So the only question left for your squad to answer is, what exactly is your platform going to stream? Get out there, start building, and we'll see you in the next explainer.